Okay, I thank you to the organizers for putting on such a conference in such unusual times. Uh, as David said, I am from the Center for Computing Sciences, which you can see behind me. No, I'm not giving the talk from the parking lot. I have a green screen, which I finally figured out how to use about 5 minutes ago. So what I'm going to go over in this talk is sort of the evolution of the idea of pseudoprimes and the related topic of probable prime tests, and where we had gotten to around 1980, and then there was a burst of activity sort of 10 to 25 years ago related to quadratic tests, and I'm going to describe that in sections 2 and 3. And then I'm going to address an idea that arose, I think it was 13 years ago, it'll be on the slides, to reduce the running time, assuming the extended Riemann hypothesis. And I'm going to describe how one can reduce that running time without assuming any conjectures. So as I mentioned in the Discord chat, this is my favorite theorem, Fermat's little theorem. And you can express it either of those ways. And the second tends to be more convenient for talking about probable primality tests. And there's the Fermat test, which where you make this very quick computation, and if it fails the test, you know it can't be prime. But if it passes the test, there are a relatively small number of false positives, which we call pseudoprimes. If you omit base A, we're generally talking about base 2. And they are what people call pseudoprimes because there are these other types that I'm going to describe. People refer to them as Fermat pseudoprimes. So some numbers, like the password to the other Zoom session, are pseudoprimes for all coprime bases. Those are called Carmichael numbers, and 1993, Alfred Granville and Pomerantz proved that there were infinitely many of these. So part of the idea of strong pseudoprimes is that you can show that there are no numbers that are pseudoprimes to all bases if you do the strong pseudoprime test. And basically what you do is you take advantage of the fact that you have the number 1, and you're raising, since you're raising a to p minus 1, you're raising it to an even power. So if you divide 2, you can divide 2 out of that power, and keep doing that until you either run out of 2's to pull out, or you get -1. And if you get something other than -1 as the square root of 1, you know that you're not working modulo a prime. And this was developed independently by Dubois and Selfridge, and Selfridge is most associated with this. So back in the 1960s and 1970s, when you'd factor a number, you'd want to know whether the numbers were prime. And so there were no fast primality proving algorithms at the time. So you'd run the strong pseudoprime test to be pretty sure that you had gotten it down to the prime factors. There's theorem due independently to Monnier and Rabin that said that it could be a strong pseudoprime for at most a quarter of the bases. And so what this means is that you don't have any so-called strong Carmichael numbers. And if you have a number and you really want to increase your certainty that it's prime, but you're not willing to do primality proving, you can pick a random base, and each iteration will be independent, and your probability that it could fool the test drops from 1/4 to 1/16 to 1/64, and so on. By the way, I should note that this is called commonly, particularly in computer science, the Miller-Rabin test, which is one of the reasons why you should probably not name things after people, because Miller did some other cool stuff, but not this particular theorem. You can think about other ways of, one way of creating your own probable primality test is you find a characteristic that primes have, and you test to see if your number has that. And the two things that need to be true about this are, on the one hand, it has to be a quick calculation, and on the other hand, it has to be fairly rare that you get a composite passing that test instead of a prime. So there's one thing you can prove is that depending on the value of p mod 5, either f sub p plus 1 or f sub p minus 1, where f sub k is the kth Fibonacci number, that's divisible by p. And so a composite satisfying this test is a Fibonacci pseudoprime. And just as repeated exponentiation makes it really fast to do the Fermat test, there are fast ways of doing the Fibonacci test, and it in fact takes about twice as long as the Fermat test. So there's a particular class of these. So the question sort of is, well, why don't you use both tests and see if things go faster? And, or not go faster, but are stronger. And so there are a particular set of conditions that Bailey and Wagstaff and Pomerantz, Selfridge and Wagstaff came up with in papers published in 1980 that said if you have a strong pseudoprime to the base 2 and a Fibonacci pseudoprime, and n is 3 or 4 mod 5, then we call this a Bailey PSW pseudoprime. And so none of these are known, I should point out, and it's not for lack of trying. It became known as the $620 problem to find one of these. And Pomerantz in 1984 published a heuristic which modifies the Erdős heuristic for Carmichael numbers, and it's a fairly convincing argument that there are. In the 90s, Red Alford and I did the first half of the computation where you find primes, some subproduct of which is probably going to be one of these examples, but then identifying the subproduct is computationally infeasible. So I'm going to describe a newer type of test, and this is the quadratic Frobenius test. And I'm going to go through this fairly quickly so I have time to get to the new results. But first, you do some trial division, you make sure you don't have a perfect square, and then you choose a non-residue, and then you choose parameters A and B, which will essentially define your quadratic field that you're going to be working over. Or again, it's a field if it's a prime, it's not if it's not. And this needs to be true. You can show this is true if you have a prime, and that is true. And then you do a similar thing where you have, you're computing roots of 1 and you shouldn't get -1. And so why, what is the point of that test? And the point of that test is that it's a randomized version of the Bailey PSW test. And so the idea was, well, the idea originally was to prove that it was at least as good as doing strong pseudoprime tests, but it turns out actually to be in a very specific sense better. So the strong pseudoprime test requires a certain number of modular multiplications, and that the unit of time is named after John Selfridge. It's called a Selfridge, and Oliver Atkin came up with this term, but he had a somewhat different formalization, and he distinguished between modular multiplications and modular squares because modular squares are often cheaper. And it annoyed him that I was using a different one, but oh well. Both the original quadratic Frobenius test and the reformulation that I described to you takes 3 times as long as the strong pseudoprime test. And remember, I said if you did 3 strong pseudoprime tests, your chance of error drops from 1/4 to 1/6 to 1/64. And I was able to show in my dissertation that a composite number can pass with probability at most 1/7710, which is a smaller number than 1/64, which is sort of an indication that there really is something going on there with the Bailey PSW test in terms of being a stronger test. And there's no, unlike with the strong pseudoprime test where there are known examples for a quarter, this is not known to be sharp. And there's the comparison I mentioned earlier. So you could also ask what the probability, if you pick a random number that it will pass the test is. That's a different question and one that I'm not going to address, but there are papers on that if you want to see. Damgaard and Franzen, and I apologize, I'm missing a diacritical mark there. In 2006, I guess it was, published something they called the extended QFT, and it has a better error probability. And in fact, well, you can see what happens as you do T iterations of it. And so one improvement was the error probability, which, as I mentioned in the last bullet, uses properties of 24th roots, which is cool and not something I'm going to talk about here. But they've also dropped the running time to 2 Selfridges, and there's a startup cost of 2 Selfridges. But so it's faster after you take into account the startup time, which is required for the 24th root part, but you have to assume ERH if you want to believe that runtime. So they actually don't use Selfridges. They cost in terms of modular squarings, and they use a factor of 1.3 for how much more it takes to do a modular multiplication versus squaring. I will note that Atkin had a different opinion about it. I think he costed us 2, it's in my paper on this, I've forgotten what it is, but one of the reasons that I never distinguished between those in the original work was it's dependent on the architecture you're using, and I felt like I was doing math and not computer science. Anyway, so you can look at this in terms of modular squares, and they still come out ahead if you look at it in terms of modular squares. And I mentioned what I described earlier was a reformulation. That the way it's reformulated actually pops up the cost in terms of modular squares because you have more multiplies and fewer squarings. So the way they improve it is basically the way, remember I described that you pick an A and B so that you have a quadratic field to work over. Well, if you know the extended Riemann hypothesis is true, then you're guaranteed to be able to find a small non-residue, and then you just use that to create your field. And then since you have that, if you want to square X, if you want to square any number or any element of this quadratic field, you can subtract rather than multiply, and subtracting is a lot faster than multiplying. So this is, when I say the same technique, what I mean is it doesn't, you can use the same technique on the original quadratic Frobenius test to get the improvement, and it reduces the running time to 2 Selfridges. But unfortunately, if you're like me and you like to do things unconditionally, you can't guarantee getting a very small C without the extended Riemann hypothesis. But what you can do is if you can bound the power for which you're having to do your multiplies, then you can cost the multiplies cheaper. So in particular, if you can get it below n to the delta, if delta equals 1/2, then it'll take half the time, etc. And so then, because in the original formulation, you're only doing one modular multiplication that isn't a squaring, you can, you basically, you have to add that delta there. So how small can you find it? And essentially, the key to this whole ball game is this lemma. The answer is delta is greater than 1/3 times the square root of E, and then a positive proportion of the numbers are either non-residues, or again, since this might be a composite, you could get the Jacobi symbol 0, and if it's 0, you have, congratulations, C has a non-trivial GCD with n, and not only have you proved it's composite, but you factored it. So the proof is fairly easy to do once you have the right pieces in place. There's if you use you have to use the correct character sum due to Burgess, because if you use one of his earlier papers, you get a result, but it's not as good as this result. Basically, to show what the character sum looks like. And then there's a result of Granville and Soundarajan that Banks and co-authors quoted in a 2008 preprint, but by the time the Granville and Soundarajan paper had appeared, they modified the result to something that I can't use. So that's why I'm quoting it. Gives you, allows you to convert from this character sum estimate to this idea that the sum is growing smaller than a constant times x, which means that a positive proportion of them aren't ones. So so this gets you down to 2 plus 1/3 times the square root of E Selfridges, but if you want to cost it with the Damgard-Franson modular squaring, you get 2.86, which is still an improvement on the original test, even if you use the modular squarings, which, to be clear, I don't like to do, but I think since enough people find that to be a more appropriate way to cost things, that is important. So finally, you can grab this paper from the archive. There's the URL, or pick appropriate Google keywords and you'll get there. It appeared earlier this year in the Journal of Number Theory. So if you like supporting Elsevier, you can go there. And I want to say that I could not have written the paper without Paul Pollack walking me through what needed to go on the Burgess bounds. So thank you for your attention, and I'm willing to entertain questions at any point.
Great. Thank you for the wonderful talk. Would anybody like to ask any questions? All right. I have one. This test, what's the motivation for that precise collection of steps in the test? Is it like trial and error and people figured out that this was efficient, or?
Well, so the motivation is to essentially, I guess, so some of the ones are, well, the trial division is that there's a point at which if it has a small factor, you can't prove a result that you need. And why are you primality testing something that has a small factor anyway? So you might as well do that. Similar with the perfect square. That's an easy check and it makes the theorems go nicer. And then the other steps are essentially, is just what I worked out what you wanted to do for the equivalent, thinking of it as you're trying to do a Fermat test, but you're in a finite extension field, and what would that look like?
I see.
And that's just pencil and paper working that out. What was that going to be? So,
got it. Thanks, Joshua. You're muted.
And your hand is raised.
Yeah.
I may have to unmute him. This thing's very weird. I've been.
Oh, he's good now.
Yeah, it told me I couldn't unmute myself. I was just going to ask if, is this the end of the road, or are there continuing improvements with diminishing results, or what happens from here?
So I don't believe that everyone has exhausted every last possibility about improving either the running time or the error probability. But I sort of made a decision myself at one point that I'm sick of this, but then I got pulled back in by this, here's a conditional result, and I thought there has to be a way of making it unconditional, and at least for this weaker result it was possible. But I in particular think that I don't know, if you look at the AKS deterministic test, there are probably some tricks there that would help someone who wanted to try to do something. I would love to see, I don't see any reason why the probability has to be constant, why it couldn't be decreasing, not just with the number of tests you do, but with the size of the number. And of course, it would be great if such a test, if you could get the best of both worlds would be an AKS-like test that actually had the sort of practicality that a probable prime test. And I don't see any reason why that's impossible.
Thank you.
All right, let's thank Jon again for the wonderful talk. And then